Recording is rolling. It is Thursday, October 27th, and today is a lab day. So you guys are gonna get to work with your hands. You guys got some pulleys back there. Here's like a single pulley. There's some double pulleys that can be helpful for some of the steps. You guys gonna do a few steps today. You guys got some string. There's some ring stands, and you can rig it all up like this. Of course, you guys got a spring scale here. You guys can have like this lab weight. All right, so there's some materials working on, but what are we trying to do and how does this connect to what we've been doing so far? Okay, so let me flip my screen over and show you guys part of this animation. Screen to share. Okay. All right, so how this whole animation that goes through a mechanical advantage for a pulley. Now, there are different kinds of simple machines you can rig up. There's like they go through them real fast here. Okay. So here's how the story goes. There's a couple of kids, Jack and Jill, who are trying to fetch water from this well, but the pail is too heavy. Oh no, they can't pick it up. So they think, hey, maybe we can do some kind of physics something. So they try this inclined plane. That didn't help. So they tried the screw. That didn't help. They could have used a gear system. I guess they didn't think of that. But hey, how about a pulley? So they throw up this single pulley. They throw the rope over, and that didn't help either because all it does is change the direction of the force. That right there is called a one-to-one mechanical advantage, which is not really any mechanical advantage at all. Right? All they're doing is right. So if the bucket weighs 100 newtons, they still have to pull with 100 newtons of force. Right? But they can get fancier with this. So they have this idea, like, wait a minute, what if we like rig it up like this? Now, do you guys see how this is no longer a fixed pulley, but it's able to move up and down? Right? You guys see it can like move up and down, right, as she's pulling this up and down. Right. So suppose this bucket weighs 100 newtons. Right. What is the force, the tension force in each strand right here? And it's not 100 newtons anymore. It's what? 50. You guys see it splits 50-50, right? Which is consistent with a spring scale lab I had you guys do a long time back. You guys remember, right? 50-50. Hey, that means that she only has to pull with 50 newtons of force. So she's effectively multiplied her strength by 2, right? She only has 50 newtons she's pulling with to lift 100 newtons of weight. Okay? So that's called a 2-to-1 mechanical advantage. Now, there's a way she has to pay for this, which is in the length that she has to pull. So if she pulls 2 meters of rope, the bucket only moves up 1 meter, right? And if you multiply force times distance on her end and on the bucket end, those should equate, right? So she pulls 2 meters with 50 newtons, that's 100 joules. Meanwhile, the bucket 100 newtons lifts only 1 meter, that's still 100 joules, right? So the input and output energies match. The work in equals the work out, right? Now, so there's your single fixed pulley. That's the first thing you tried. Here's a single movable pulley. That's the one that ended up working. Right? Multiplied your strength by 2. Right? So by the end here, they rig up this this new system where, hey, what do you think her mechanical advantage is for that type system? What's her strength being multiplied by? Well, let's take a look here. So I see this bucket, right? Being held up by, let's see, got this movable pulley that, oh, hey, how many ropes do you see? 1, 2, 3. Do you guys see 3? Of course, there's only one single rope just wound around and around. But isn't the weight effectively split 3 ways? So if the bucket, again, like weighs 100 newtons, it's probably about 33 newtons in each strand, and she only has to pull with about 33 newtons. You guess that? Like a third of it? So she's like 3 times as strong. Now, again, there's a catch, and the catch is that she has to pull 3 times as much rope for like every meter that the bucket goes up. So the bucket to lift the bucket 1 meter, she has to pull 3 meters of rope. Okay, you guys get that? All right, so let me switch back over to the setup. Okay, and you guys have here. Let's go through what we just went through. Okay. Look at the example that I'm giving you guys here. What mechanical advantage is this system that I drew right here? What mechanical advantage is that? Right. 3 to 1? 3 to 1? Because look, here's the movable pulley. I got a couple of fixed pulleys. These are fixed in place. Okay. But this one's movable. It's going to move up and down with this weight. And look, 1, 2, 3. Of course, it's only one string, but the string like splits the weight 3 ways. Right? Ooh, do you guys think that whatever weight this is in newtons, the spring scale rating is probably about a third of that? Right? I bet it would be. Of course, you guys are going to find out for sure when you do this later today. Right? So everybody should have this lab page. I didn't miss anybody, right? Everybody's got this half-page lab page. You guys got this? Right. Double-sided. I'm going to have you guys set up 4 different systems, right? 4 different pulley systems. A 1-to-1 mechanical advantage, a 2-to-1 mechanical advantage, a 3-to-1 mechanical advantage, and then the challenge one's gonna be a 4-to-1 mechanical advantage. Right? Back in the lab area, I do have a 5-to-1 mechanical advantage set up. It's actually been there since the first day of school. Right? So help you guys out a bit here. What we have you guys do is draw the system that you set up. Okay, here's what a 1-to-1 looks like. Here's what a 2-to-1 looks like. Okay. Ooh, there's a movable pulley here. Okay. And of course, I'm going to leave this 3-to-1 up during the entire class, so you can use the 3-to-1. You can play off that. Okay. And let's run through the physics, right? Because this connects to what we've been doing all this week, which is conservation of energy. Right? Now, why is this conservation of energy? See, you can't multiply the amount of energy in the system. If you could, that'd be really nice. Then you could just run the entire world on like one lump of coal. But it don't quite work that way. Right? And for that principle, same principle, you can set up this type of equation. Right? So energy is conserved. That's to say that the work that you put into the system is the same work that you get out, which is so force times distance in equals force times distance out. Right? And the input is all on the end of the spring scale. Right? You agree with the spring scale with, right? So that's force on the spring scale times the length that you end up pulling. Okay? You guys think you could put either a ruler or a meter stick up next to this right here and see like how far you pull it, right? And then you can put a ruler or meter stick up next to this weight and see how far the weight moves, right? And if you compare these things, right? This weight times the amount of height that moves is the output work, right? But the input work should match the output work. At least that's the physics theory, right? And you guys can see how close that is. Okay? And mechanical advantage ends up being sort of by definition the ratio of the distances, right? So the length pulled compared to the height change, right? That might be like a 3-to-1 ratio for this one, a 2-to-1 ratio for this one, and a 1-to-1 ratio for this one. Okay. But do you guys think that it's possible that maybe if these strings aren't exactly vertical, or if there's some frictional forces, that this might be a little bit lossy, and maybe you're not going to get exactly the full mechanical advantage? Right? So if you compare the forces, right? So what is this weight compared to this force reading? That's the actual mechanical advantage. And these should be pretty close to each other, but they might not be exactly the same. They might be, but they might not be. Right? And if they're not, you can calculate efficiency by taking the ratio of those. Right? So what have we got on the lab paper? I'm gonna have you guys draw your system. Right? In fact, this picture you just copy paste right here for the 3-to-1. Right? Record what's the weight that you use. Right? Now, guys, the weight you use, you have to measure in newtons, right? Let's do an example. The largest lab weight you have back there is 1,000 grams, which is how many kilograms? That's 1 kilogram. And that weighs almost how many newtons? You could round to. Is that 10 newtons of weight? Okay. So in fact, if you just want to grab the 10 newton weight, I mean, you don't have to, but you could. You could just use the 10 newtons over and over again. You just click that right there and just call the weight 10 newtons. 10 newtons. Right? Okay. So what's the force reading? That's going to go straight from the spring scale. Right? You can hold the meter stick or the ruler next to each one of these. Say what's the height change for the weight, and you could either do centimeters or meters. And then the length pulled, you could also do centimeters or meters. Just make sure you use the same unit. You're consistent. Like you could do both meters or both centimeters, right? And then ideal mechanical advantage and actual mechanical advantage. I'll have you guys calculate those using these equations right here. And I will leave these up again. I'll leave this page up over the class, right? So you can reference this page, right? Who's got any questions? Any questions? All right, guys good? All right, so I will be walking around lab area helping you guys out. You guys have the rest of the class to work with each other, get your hands on these materials, build these pulley systems. So enjoy.